To start off our presentation, we want to introduce you to our clients. Our primary client wants us to develop a method and apparatus to record and control impact events. Our secondary clients would be our instructor, Dr. Becknell, as well as the grader, looking at our impact control experiment. The metrics of success in order of customer preference include providing time-resolved acceleration, velocity, displacement, and force data, must match peak impact signal magnitude across all tests to within 5% of the average value. At least 20 data points must be present in a measurement pulse. More is better. A high signal to noise ratio is desirable. Measure what's important, minimize disturbances. And ease of training novice users to conduct good experiments is desirable.
For our house of quality, we can see that it's broken up into several sections. Starting off, we have our functions and constraints, or where it says what's. These include creates impact, controls impact, measures data, records data, withstands impact, and is reusable. These are all things that the device, for a function, it must do to be what it is, versus the constraints, which are things that it should do to be what it is, like having paint on a bike. And then you also have the hows, which include all of our units like newtons, acceleration, displacement time. Everything that we need to collect is going to be in this section up here. In the very top, on that top triangle, you have all of the correlation between those units. And then in the middle, in the red, is where our relations are between our functions, constraints, and those units. From this, we can infer that the customer wants a few things for its impact control experiment. First of all, they need to measure the impact. To do this, we need to record the impact, but have a consistent environment. In this, we will record 20 data points and have a way to display the data. Secondly, we must create the impact. It must be able to withstand multiple impacts, protect the device, and be reusable.
Now for our first alternate design, we came up with a drop test pulley system. You pull the string and it raises the device to a certain height. As you drop it, drops down onto a foam block. But unfortunately, we found that this did not produce our 20 minimum data points that we were looking for, and it's also just kind of complex to make. For our second alternate design, we came up with a wheel roll test where a tire or bike wheel rolls over multiple recording devices, recording at the same rate, the same time. Now this one would have produced our 20 minimum data points, but it's just a bit variable in its tests, as you have to make sure all of the recording devices are recording at the same rate, which is easier said than done. For our first iteration, we came up with another pulley design, but in this case, the device drops down on a rubber band trampoline. This would have allowed us to get our 20 minimum data points, but as I mentioned earlier, it's just a bit complex to build, and we could make it much easier. Now for our second iteration, we thought we could blow up a balloon and put it into a hardware bucket where we would drop the device onto the balloon, similar to the rubber band trampoline. The only difference is the balloon is much more bouncy than the rubber band trampoline, so we didn't think it would give us our 20 minimum data points. And now for our final design, we decided to keep the bucket, but instead of using a balloon, we went back to the rubber band design and put rubber bands over the top of the bucket. We also created a carrier that would allow us to put our device that is recording the data onto a weighted kind of bowl, and we would fasten the device with 2 rubber bands. As you can see on the left is a top view, and on the right is a side view, and we would drop the device from a set height, and this ended up giving us our 20 minimum data points and allowed us to continue with our project.
To expand on why we chose our final design, we wanted to look at a few things. First of all, our functions and constraints. We use these to find the geometric average of each using this formula. After this, we continued by normalizing the criterion, in which we used this formula. Using the normalized weight for each function and constraint, we were able to narrow down which design met our goals. We have design 1, design 2, And design 3.
Now, as you can see, we have a 3D animated video through Fusion showing us how to use our device. So you just take the bucket that holds the recording device, take it up onto the top of the third bucket, which is where we are going to release from. As you can see, there is a small window so we can see what's going on inside. Then we just go ahead and drop the bowl, goes down, comes back up with the rubber bands. So this is the inside of our device. There is a measuring tape that measures the displacement from the actual rubber bands of the trampoline, and we record this data with an outside phone recording the inside of the bucket. We place, like I said, the device recording on Firefox on our carrier device, and it drops down and we get the displacement data from there.
For our data acquisition process, we needed to do a few things. First of all, we needed to set up the 3 buckets in the orientation so that they're stacked on top of each other in order for us to get a repeatable and continuous drop height. Second, we needed to place a phone within the rubber bowl which would be dropped onto the trampoline section of the device. This was needed so that we could collect acceleration and velocity data as well as displacement. Third, we needed to weigh the bowl and the phone to see how heavy the thing was so that we could collect the data and do the correct calculations. Next, we needed to place a second phone and a ruler within the bucket. The ruler's purpose is to measure the total displacement of the rubber bands at the moment the drop device hits the trampoline surface. And the phone was used to record that displacement. We then would open the Firefox Lab and prepare to record. We used a remote device or a laptop to remotely start the trial on the phone that is dropping, as well as the record feature on the secondary phone at the bottom. We would then release the bowl at the top of the buckets, and then we would record all this data and place it in Excel. With this data, we were going to calculate acceleration, velocity, displacement, and force. And then we would take that data from the curve in the acceleration graph and we would integrate it. We can now look at our graphs that we have derived from the data that we have collected, which was plotted in Excel. To the left, we can look at our acceleration versus time graph, in which we have an initial spike in between 3.7 seconds and 3.8 seconds. This spike represents the initial drop from the top of the tower. We can then see that our acceleration flattens out as a result to gravity as the bowl falls. We then can see around 4.1 and 4.2 seconds that we have a large spike in activity in data point. This represents the impact of the dropping device into the trampoline section of the tower. We can now divert our attention to our middle graph, which represents velocity versus time. As we can see in this graph, in between 3.7 seconds and 3.8 seconds, there is that initial spike like before. This represents the start of our trial, which is easy to track throughout the graphs. We can then see the flat section where the velocity is constant until you have that final dip in data points representing the impact and drastic decrease in velocity as the drop device impacts the trampoline and is slowed down by the rubber bands. Now, if we look to the right, we can see our displacement versus time graph. Like before, it starts right around 3.7 seconds, and then right after 4.1 seconds, we can see the steep decrease in points as it follows down the chart, indicating that we have made contact with the trampoline and the displacement has decreased as velocity and acceleration all fall. And for our final graph, we are going to be looking at force versus time. In this graph, you can see like before, at 3.7 seconds and 3.8 seconds, you have our initial drop from the top of the tower. As the device falls, force becomes 0 as there is nothing but gravity acting on the device, which is not measured in the Firefox app in this case. Then, right before 4.1 seconds, you can see that the impact of the device on the trampoline was slowed down in between 4.1 seconds and 4.2 seconds, plus minus half a second on either ends. and we were able to collect 20 data points and some during this impact. Now down below, you can see that we have 3 categories: adults, time, and data similar. In the first category, this represents the 5 adults that we have asked to conduct the same level and quality of experiments that we have documented in this presentation before. This means collecting all of the data, being able to get all 20 data points for all of the given values, and being able to do it efficiently and accurately. As we can see, the range was between 14 minutes to 17 minutes, ranging from fastest to slowest of the adults conducting the experiment. Now to look at the results from our testing. We determined that the total time that the impact took place was from 4.07 seconds to 4.25 seconds. This was determined using the acceleration data and the curve shown in the graph. Next, we looked at the slow video displacement. We determined that from the top of the trampoline to the final Y position of the trampoline and bowl would be about 8 inches, give or take 0.15 inches. Next, we looked at the integrated displacement, which could be determined from the top of the device to the very bottom. We determined it to be plus minus 0.3 of 0.8 meters. After this, we looked at our acceleration peak percent error. We determined that in between experiments, it was around 5 to 15%, a little higher than what we want, but not the worst nonetheless. Then we can look at our average data points. Per trial, we determined that we were getting exactly 20 data points. This was constant each time, every time, without fail, which is exactly what we were looking for. And then for the surveys conducted, we used 5 adults, and it took about 18 minutes to produce similar data. Now to look at our signal processing. First, the exact place and height for the bowl and phone when measuring was always the same. This helped getting those 20 data points consistently and having our values and data be within 5 to 15%. We then used an exact time to record data for the time drop in order to reduce extra data or noise in our data and graphs. Then this allowed us to calculate standard deviation while also taking into account for other forms of noise, such as inaccuracy in start time or Wi-Fi errors.
Some improvements to be made on our device include 1. Using a rope instead of rubber bands for the placement of the carrier device. The rubber bands proved to make it harder to pick up the carrier due to its weight, so using proper string or rope next time would help with the ease of use. Next would be to use a sensor for exact displacement and velocity instead of using the measuring tape so we can eliminate the possible errors of integration. After that, we can file the nails inside of the bucket in order to prevent any snagging and the bending of the rubber bands. And we can also place the camera further up to reduce the noise and data due to the angle of the camera it was recording at. And finally, we could replace the cheap rubber bands with higher quality rubber bands in order to collect more data points, as the bands we used made it difficult to lengthen the impact event.